Hi everybody, I'm Bhaskar Saha from the Palo Alto Research Center, and today, continuing the theme of resiliency, I'm going to talk about constraining Murphy's Law. So Murphy's Law, anything that can go wrong will eventually go wrong, and things do go wrong. We are all familiar with these things. Here are a couple of examples from the automotive domain, clutches and brakes. They have different kinds of behavior during fault. Clutches slip, they judder, they shake, brakes get worn, mushy, grabby, slack, and we know what to do about these things. We can analyze these faults. You can set up experiments, gather data, fit models to them, and even predict. It's tough but doable. But what happens when you scale up? You go from components to systems of systems. The space shuttle is 2.5 million components plus. Fault analysis becomes extremely tedious and painful because now you have to peel back layers upon layers of system behavior to get to the real fault behavior you're interested in. Here's a plot that shows how it actually scales. You have number of components on the x-axis. On the y-axis, you have the number of faults. It grows polynomially because you not only have multiple fault modes per component, you have faults that arise out of interaction between components and even communication between components. So the number of faults can just blow up on you in a big enough system. But there is a silver lining to this problem. If you dig really deep down to the root cause, to the physics, the number of root causes is limited, it's constrained. Anytime you add one more component to your system design, you have already accounted for perhaps most of the root causes that will cause failures in that component. So that's represented by the orange-red arrow that you see near the bottom of the curve. So as your faults keep growing, the number of root causes that will cause those faults kind of level off. So is this true? Let's investigate again our friends, the clutches and the brakes. Here I've grabbed a couple of descriptions of these models from the Modelica standard library, which is used in automotive modeling in Europe quite a bit, and now starting here in the US. Let's look at the equation in blue over there. It equates something which is a torque on the left hand side to a product of a coefficient of friction, a geometric constant, and a force. It's exactly the same in the brake. So what that means is that when you dig into the root causes, what affects coefficient of friction? Well, friction wear. What affects the geometric constant? Fracture. Maybe it happens both in the brakes as well as in the clutch. You can have shoes that fracture in the brake. What about Fn, the force variable? Well, they get affected by loss of hydraulic pressure, maybe due to a leak. They get also affected by fatigue in the spring force. So can you analyze them in a formal manner and pre-populate the faults in it? Here's an example just for friction wear. Again, you have multiple modes here. We preserve the normal mode, the equations that existed before, and we went in and added one extra mode called worn. What happens there? Well, look at the last equation. The torque variable tau gets multiplied by it's a product of mu of CGO and Fn as before, but now the coefficient of friction mu is modified by a slip factor, which is a product of a wear rate of the force, normal force, and a sliding distance. And then those are the parameters for your fault, but sliding distance is different for a clutch than a brake. So for a clutch, it is the number of shifts times the time for each shift time the difference of angular velocity. For a brake, it includes the braking time and the speed of the wheel. So there are some fault specific factors and there are some component specific factors in there. So in this way, we can redefine the problem for us. You don't have to peel back layers of system behavior, but you can construct them as you design your system in a very systematic way. And you can intelligently identify the fault locations, you appropriately parameterize the physics and you insert them there. What does it mean? Well, it means that you can reduce your manual effort by 80 to 90%. Fault analysis can now be done for large systems. You can analyze more faults, and this is reusable. Means that when you build in, update your designs, you bring in new components, you can reapply the same procedure and have your fault analysis done. So at the end game, fault analysis, this kind of fault analysis makes your designs more resilient. And this is now, we are doing this for DARPA now for the adaptive vehicle make. What can we do for you? Thank you.